Hello everyone, my name is Varun Chaudhary. I am a senior research fellow in School of Material Science and Engineering. Today's class will be focused on physical property measurement system. Our special focus will be on VSM option attached to the PPMS since the class is on magnetic materials. These are the outlines for today's class. We will first cover the basic components of the VSM attached to the PPMS, sample preparation, installation of the VSM to the PPMS, sequence writing, and at the end, we will consider few examples what can be measured in the PPMS. So the development of vibrating sample magnetometer is associated to this paper published in 1959 by Simon Foner. The primary components of the VSM is electromagnet, mechanism of vibrate the samples, pickup coils, and of course the electronics to measure the voltage in the coil. So here the basic components of the VSM are attached to the PPMS. The main difference between conventional VSM and the VSM which is attached to the PPMS is that in conventional VSM we use the electromagnet while here we use the superconducting solenoid magnet and the field is in transverse direction and the pickup coil and the linear transport motors also known as the VSM head. So the superconducting solenoid magnet is somewhere here in the system. The pickup coil go inside the superconducting solenoid and this linear transport motor is here. So the physics behind the VSM is primarily governed by Faraday law of induction. Induced voltage in the coil is proportional to the time derivative of magnetic flux through the coil. This voltage is proportional to the amplitude of the oscillation, frequency, and of course the magnetic moment. Typical measuring unit for the magnetic moment here is in CGS unit, which is in EMU. However, it can be converted into the SI unit and ampere per meter square, ampere meter square. So the sensitivity and the sample size. So basically the sensitivity of this, it depends on which coil set you are using. There are two type coil set we have. One is standard coil set and the other is large bore coil set. Standard coil set sensitivity is 10 raised to power minus 7 EMU and we can use the sample size around 4 millimeter square. It depends on the diameter of this. So if the sample size is more than that, then there is a chance that the sample can get dropped to the coil set. In the large bore coil set, the sensitivity is relatively low and we can use a relatively bigger sample. The sample environment can be controlled in the range of plus minus 9 Tesla magnetic field. The temperature range is from 1.9 Tesla to 400 Kelvin, 1.9 Kelvin to 400 Kelvin if you are not using the oven. If you are using the oven, then we can extend this range up to 1000 Kelvin. So these are the sample holders, how we prepare the sample, how we mount the samples. So there are many kind of samples holders depending on what samples we are having. If we are having a thin film sample, then a quartz sample holder is used. If we are having a powder or bulk sample, then we use the copper base holder. So to prepare the powder base sample, we first wrap it in the Teflon tape and then fill this wrapped sample inside the capsule, polymer capsule. So these capsules are especially designed that they are non-magnetic and we can use them especially for low temperature measurement up to 400 Kelvin. Then mount it here and apply some GE varnish. We should be very careful that the sample should be somewhere here 35 millimeter. This is because it's designed that if we set the sample here, then it will be at the correct position in the pickup coil. So for high temperature measurement, this is a special sample holder, which is the heating element is inside that, and which is heated by up. And in this case, we use the copper foil and white cement, as we cannot use the GE varnish to mount that thing. So installation of the VSM option. So before installing that, we should first make sure that the temperature is at room temperature and magnetic field is set to 0. That I'll let you know in coming course how to set this field 0 and temperature to room temperature. And this is the sequence. First we install the VSM coil set, and then guide tube, and then VSM head, and then motor and VSM modules. So this is the video here you see. So this is the pickup coil. Then I'm installing it using this tool. This tool is something that it can clamp it from the top and it will not fall down until unless you lose it from top. So now the coil is going inside the chamber. After that, once it touches to the bottom, we just rotate it clockwise or anti-clockwise, doesn't matter. Then and provide a little force downstream. Then we'll hear a sound. Then we can place the coil here, and then take the tool out. Then next we need to place the guide tube. So this will go in. I'm installing it. The third is to install the VSM head. So let me bring that head. So the VSM head had about 4-5 kilogram weight. So we should be very careful for that. And just put it here, clamp it properly. And now I'm clamping it. Once it is done, the next is we need to attach the motor module and the VSM module. So now I'm attaching the motor module first. So there are so many cables here. We have given the name, tag the name there. So this is, I have attached this motor module, and this is, now I'm attaching VSM module. Yeah, so now this is done. So now we have installed the VSM coil set, guide tube, and install the VSM head as well as the motor and VSM modules. Next is loading the sample. So to load the sample, just what we do, this you see here that we have a long sample tail, and then this is the sample here. It's going inside slowly, and at the top here we have this portion has a magnet, and here also magnet. So once it comes to the close, it attracts to each other, and you'll hear a sound click. Now just cap it, which is required to have a vacuum if you want to do the low temperature measurement and all. Yes, now the sample is already in. Yeah, so here is the activation of VSM option, software side. So what we do here, go to the utility, active option, and there are so many options. Just select the VSM, activate it. So it takes around a minute to get activated. It check internally whether we have installed all the modules properly or not. It check the motor vibrations and take around 1 minute to check internally. So till the time we can understand that the helium level we have currently 98.3%, and the battery supply should be in green mode. That means our bottle supply is correct. Yes, so now you see that the VSM is ready and we can use the VSM now. So yeah, just click to install and remove. So yeah, a new window will come up, open chamber to load the sample. However, we already loaded that sample in. So our sample is already inside the chamber. So we can move to next. Yes, next. Then here we have two options, standard VSM or oven VSM. So, we are using the standard one. We have not discussed much on the oven side. So standard and the next, and for the next. Now we need to give the name to the sample and mention the property about the sample. So I'm just saving it on the desktop, giving a name. Okay, let's say demo, and then open. We need to copy it because we from here we need to write this in many places, so it's good to have a copy. Then you can write and give the same name here, just paste. Material name same, yes, I'm giving the same name. In the comment also can be the same, and the sample mass. So yes, the sample mass is important. Before loading the sample, we must know how much is the mass of the sample, and we need to write it here. If it's a thin film, then we need to write the volume. If it's a bulk, then mass, bulk of particles. So everything is settled. Then go to the next. Then now is we need to scan for sample offset. Whether as I mentioned earlier, that this should be at 35, close to 35 mm. So for scan for sample offset, we need to provide some field, a small field on the sample. Then the system will automatically check what's the actual position of your sample. So I have set a field of 200 Oersted. Once it reach, here you will see that value. Then we can scan for sample offset. Yeah, so now its field is 200 Oersted. Now scan for sample offset. Now system is checking that whether the position of the sample is close to 35 or not. So it will again take 30 to 35 minutes, 35 seconds. And then one thing is that we should take note on that when the system is doing some measuring or calibrating itself, we should not click. Otherwise, it will hang and everything need to be done again. So just relax because the system is very complicated. The software is very heavy and complicated. So that's it. Now it's showing something. It has measured showing that it's close to 35.06 millimeter. It is acceptable. So basically we see 34.5 to 35.5 is acceptable here. Then go to next and close the chamber. So in case you just want to measure the properties at room temperature, you can simply close the chamber. But if you want to do lots of measurement on this sample and for low temperature measurement, low temperature MH, low temperature MT, then it's advisable to use the extended purge and then close the chamber. So it will purge this multiple times. Yeah, it will again take some time to fix. So one by that time, so now our value was 35 point something, 35.05. It's acceptable. If let's say this value is below 35, 34.5 or above 35.5, then we need to take the sample out and then again need to fix the position correctly and again check the position. This is how it's advisable. Yeah, so it just purging it. Here you see some underdefined, and then yeah, here you see that now we can press it this finish. However, even after pressing the finish, you see the system is still not sealed. So prior to start any experiment, we should wait here till here we see the shield. Otherwise, we will be having some additional error or something. So we need to wait here till the time it gets sealed. Then we can start our experiment. Start button is here. Before that, we need to write the sequence, of course. Okay, it will be sealed and just we can go to next slide. So yeah, now we will show here that how to install the oven for high temperature magnetic measurement. So this is a very sophisticated system. It's a very small tool you see here, and it permits the system to reach up to 1000 Kelvin. I'm just installing it and just a finger tight. That's all. Now next is here we need to attach the oven module. Yes, that is done. Now let's install the sample. Yeah, this is sample holder. So this is, you see, is different kind of holder, and it has some attachment on the top. From the top, it will heat the sample through here, through the tail. Now the sample is going in. Now few pin here. That's just I'm attaching it, and then close the cap. That's done. So high temperature measurement, we need a high vacuum and 10 raised to power minus 7 torr. If the vacuum is because of some reason system cannot generate that high vacuum, then we cannot measure the magnetic property at high temperature. So next is how to write the sequence for VSM and to do the measurements. So for that, just select the template sequence and edit that. So here I have selected, and you see here, so the first line, just we need to edit it and browse the sample name what we have just generated, the demo, and append to file. The second line is set magnetic field 0. So before doing any measurement or write any command, we first need to set the field 0, and the ramp rate can be anything 100 or less than that. The next line is we need to wait for some time
after every important sequence. For example, the sequence was just set temperature, set field, and then the next is wait for 60 seconds till the system reach exactly close to the field what we have set it here. And the next it should be the temperatures, set temperature 300 Kelvin. However, it's already set, but we still need to write the sequence here. So I just written here the set temperature 300 Kelvin. So after that, we again need to wait. So we can just copy paste from the top, just below that one line, that wait for temperature and field 60 seconds. The next is to write the VSM sequence. The field can be up to 9 Tesla. So here I have a 1 Tesla field, and we can have here whether we want to measure it's a complete loop or we want to just measure the first quadrant or all. So we just select and drag. So I have selected starting from 0 to maximum and the minus minima and then the maximum. Field rate, it can be anything. If you want to measure quickly, then it's 100 Oersted or 150 Oersted. If your sample is really important and you let's say it's a very low coercivity sample, then the value can be low, say 2 Oersted or something like that. This is in advance. Set the no automatic centering, and then yeah, these are here what we have. It's a disabled sequence. We don't want this. If you want to measure these things, we can enable them just by right clicking and then enable. So we need to save it. You see we have a star here, so that means sequence is not saved. Just save it, the star will go away. And then run. So you see here, you will see the which number of sequence is currently running line. So here we are on the second line, fourth line. So go to install. So this is the same window, we install it, data file, and see the view. So it's the new window will come up. You can select the data. I mean, let's say here it was magnetic moment versus time, but we want it magnetic moment versus field. So just right click on it, select field, magnetic field, and OK. So now it's magnetic moment, which is in EMU. Later you can make it EMU per gram, as you already know the mass of the sample. And this is magnetic field. So now we are at number line 4. So it will take 8 minutes for this measurement, but before that it will set the field and temperature. So you see it's at fourth line, 1 2 3 4, meaning that wait for temperature. Now it is waiting for the temperature and field what we have set in line 2 and line 3. So the set temperature is 300 Kelvin and it's trying to reach exactly at 300, which is now 300.09, while the set field 0 and it's 0.19. So it's always some in the field it's very difficult to get exactly 0. It's because of some static field in the chamber, it's sometimes 0.1 or 0.01, something like that. So another important thing here is that the temperature ramp rate when we are measuring the magnetization versus temperature curve, should be 3 Kelvin per minute or less. However, if we are not measuring any movement and we just want to go from one temperature to another temperature, we can fix the rate 10 Kelvin or 12 Kelvin. So this is still 300.09 and line 4. So it may take some time. It may take some time, maybe 2 minutes or 3 minutes. The reason, however, here we have written the wait only 60 seconds, but system tries its best to go as close as possible to the set value what we have set here. So this is the new. Sometimes this window comes, so we just need to close it. It's not important. And then we will see the first point of magnetic moment versus field curve. See, we are already on the line 5. See, sequence run and 5, which is 1, 2, 3, 4, 5. Yeah, so we have a first point. So the rate is quite high, 100 Oersted per second. So it will the complete loop will finish in 8 minutes, but we will not wait here for 8 minutes because in the next few slides I will discuss this MH loop and magnetization versus temperature curve.
So now we will discuss several kind of materials, soft magnetic materials, hard magnetic materials, magnetic nanoparticles, and all measured in this system. So, for example, here we have a high entropy alloy type of system, and this is a bulk sample measured at different temperature, starting from 2 Kelvin to 300 Kelvin. And you see the system is at ferromagnetic at low temperature and become a paramagnetic at room temperature. And it has a very low coercivity and can be considered as a soft magnetic materials. This is a magnetization versus temperature curve used to know what's the Curie temperature of the material. We have measured it in cooling mode and heating mode to know whether the sample has hysteresis, temperature hysteresis or not. And you see it's almost overlapping both the curve to each other. That means it's not sample doesn't have any temperature hysteresis. Another information what we can get from here is that whether the sample is first order transition, exhibit a first order transition or second order transition. So it's a second order, it's slowly coming from ferromagnetic to paramagnetic. It's usually a second order phase transition. But if it's the abrupt change from ferromagnetic to paramagnetic, it's known as a first order transition material. So this is another example, hard magnetic materials. So NdFeB type of materials, you see these materials have coercivity of close to 2 Tesla. And then we measure these at different temperature. At low temperature, at 100 Kelvin, the system is at showing 20 kilo means 2 Tesla, close to 2 Tesla coercivity. And then at high temperature, the coercivity decrease, magnetic remnant also decrease. So these parameters are very useful to know about what's the strength of the permanent magnet. So from here we can get the BH max and all. So see the magnetic nanoparticles. Basically, they are the super paramagnetic nanoparticles, and we measured the MH and ZFC curve for that. So this is simple MH loop, and you see its coercivity is close to 0, which is true for super paramagnetic nanoparticle. And this is the snapshot of the sequence. It's very important how sometimes people confuse that how to write the sequence for ZFC, zero cooled, field cool cooling, and field cool warming. What does that mean? So basically, zero field cool means first we need to set the field zero, go to low temperature using any rate what you want with 10 or 12 or less, and then wait for some time. Set a small field. Let's say in this case I set a 140 Oersted, and then again wait, let's say 60 seconds, and then measure the magnetic moment with increasing the temperature. So basically here the black curve is starting from here and it go like this. Then once it reached the high temperature, we just wait 60 seconds and then again go to low temperature. Then come back. So by doing this practice, we can get to know more about our system. What's the blocking temperature, whether the system is really a super paramagnetic or not. So if our blocking temperature is below room temperature, that means we can say that the particles are super paramagnetic at room temperature. So bulk iron cobalt nickel base alloy measured the high temperature magnetic properties for this very recently measured, and you see. So here also we have done in heating mode and cooling mode using this VSM01 setup, and see the Curie temperature is above 950 Kelvin, and there is some change. There is some change in heating mode and cooling mode. This is assume is probably because of the some kind of phase change at high temperature. So yeah, here is the summary what we have covered today, what we have learned. First, we have discussed about the basic components of the VSM attached to the PPMS and their use, the VSM installation, the PPMS, sample preparation, writing the sequence, and we have also covered few different type of materials, their magnetic properties, and learn how to know whether the sample is super paramagnetic, ferromagnetic, or hard magnetic or soft magnetic. Thank you very much. If you have questions, please.